Everyone knows that special relativity is hard to understand, but why is that? Well, that's because the universe is hard. Even though it's hard to understand, people love special relativity. I mean, at least at the most superficial level. This is fine. There's a big difference between getting a PhD in physics and reading an article in Discover magazine, but the one thing we all have in common is our curiosity. So let's try to understand more of special relativity today. I'll try to explain to you the twin paradox and the garage paradox using some of the ideas that lie at the core of the theory of special relativity. As we said, if there is one defect in the universe, it's that the universe is hard. Humans have a hard time understanding it if they aren't willing to study diligently, and sometimes even if they are. There's no way around this. In the case of science, no law says that the universe has to work in ways in which us Homo sapiens can make intuitive or visual sense of. You can read an article and discover and get a glimpse. A talented writer can give you a slightly better glimpse. However, if you get a PhD in physics, you'll get an even better glimpse. You'll start to grasp simultaneity, light cones, stress energy tensors, geodisks, world lines, Riemannian geometries, and frame dragging. But will we ever be able to truly understand? Will you ever truly be able to picture it? Probably not. You might eventually be able to manipulate the algebra deftly, but at a visceral level, our brains evolved to understand spear throwing and baby raising, not differential equations of tensor analysis. Special relativity is one of the most popular famous ideas in physics. It's that the thing that Einstein figured out about the speed of light in space and time and E equals mc squared. It changed our understanding of the universe, and its core ideas are accessible in principle to anyone who understands some basic algebra and geometry. You don't even need to know calculus. Let's try to understand the twin paradox, starting from some core ideas. According to special relativity, a moving clock runs slower, so a person in a high-speed moving vehicle will get old slower. This is due to so-called time dilation. Time dilation is the slowing down of a clock as determined by an observer who is in relative motion concerning that clock. In special relativity, an observer in inertial, or non-accelerating motion has a well-defined means of determining which events occur simultaneously within a given event. A second inertial observation, who is in relative motion with respect to the first, however, will disagree with the first observer regarding which events are simultaneous with that given event. Neither observer is wrong in this determination. Rather, their disagreement merely reflects the fact that simultaneity is an observer-dependent notion in special relativity. A notion of simultaneity is required in order to make a comparison of the rates of clocks carried by the two observers. In the first observer's notion of simultaneity is found that the second observer's clock who runs slower than the first observer's by Lorentz factor, where v is the relative velocity of the observers, and c equals 299,792 kilometers, or 186,282 miles per second, so the speed of light. Similarly, using the second observer's notion of simultaneity, it is found that the first observer's clock runs slower by the same factor. Thus, each inertial observer determines that all clocks in motion relative to the observer run slower than that of the observer's own clock. Let's see where this brings us. Suppose Albert and Isaac are twins on the Earth. At the age of 20, Albert decides to start up a space trip in order to visit the nearest to Earth extrasolar pub. The whole trip takes 10 years. When he returns to Earth 10 years later, Albert is 30, and amazingly, and maybe sadly, he finds that his twin brother, much older than him, Isaac is 40. This is what the twin paradox says. I remember the first time I heard this, I thought it was nonsense. How could that be possible? It's counter nature, so it couldn't be true. But as the years were passing by, I found myself having to do with maths. I had to deal with it so much that I eventually started to believe in its power. And the math behind the twin paradox was telling me it was true. Albert could have been older than Isaac. The reason is that the high-speed motion makes time pass slower in the spaceship. Thus, t can be much younger than e. We would call this the first twin paradox. It really isn't a scientific paradox, but more of a logical one. How old is Albert? Albert has experienced 30 years of life. But he was also born at the same moment as Isaac, which was 40 years ago. So is he 30 years old or 40 years old? In this case, the answer is both, depending on which way you're measuring age. According to his driver's license, which measures Earth time and is no doubt expired, he's 40. According to his body, however, he's only 30. So neither age is right or wrong, although the Social Security Administration might take the exception if he tries to claim benefits. But the conclusion can also be the reverse. The most important part of special relativity is the principle of relativity itself. From the standpoint of t, E is in a high-speed motion relative to him, thus the clock on Earth should run slower, and E should be much younger. This is what we'll call the twin paradox 2. The twin paradox 2 is a bit more technical, and really comes to heart of what a physicist means when they talk about relativity. The scenario is based on the idea that Albert was traveling very fast, so time slowed down for him. The problem is that in relativity, only the relative motion is involved. So the question now is, what if you considered things from Albert's point of view? Then he stayed stationary the whole time, and it was Isaac who was moving away at rapid speeds. Shouldn't calculations be performed in this way mean that Isaac is the one who aged more slowly? Doesn't relativity imply that these situations are symmetrical? Now, if Albert and Isaac were on spaceships traveling at constant speeds in opposite directions, this argument would be perfectly true. The rules of special relativity, which govern constant speed, inertial frames of reference, indicate that only the relative motion between the two is what matters. In fact, if you're moving at a constant speed, there's not even an experiment that you can perform within your frame of reference which would distinguish you from being at rest, even if you looked outside the ship and compared yourself to some other constant frame of reference. You could only determine that the one of you is moving, but not which one. But there's one very important distinction here. Albert is accelerating during this process. Isaac is on the Earth, which for the purposes of this is basically at rest, even though in reality the Earth moves, rotates, and accelerates in various ways. Albert is on a spaceship that undergoes intensive acceleration to read near light speed. This means, according to general relativity, that there are actually physical experiments that could be performed by Albert, which would reveal him that he's accelerating, and the same experiments would show Isaac that he's not accelerating, or at least accelerating as much as Albert is. The key feature is that while Isaac is in one frame of reference the entire time, Albert is actually in two frames of reference, the one where he's traveling away from the Earth, and the one where he's coming back to Earth. So Albert's situation and Isaac's situation are not actually symmetrical in our scenario. Albert is absolutely the one undergoing the more significant acceleration, and therefore he's the one that undergoes the least amount of time passage. Okay, let's take a break now, because we're really tired. Here's some koala pics, and we'll give you strength to get through the second paradox of the video, the garage paradox. To explain the garage paradox, we have to introduce the first well-known concept of length contraction. The length of any object in a moving frame will appear foreshortened in the direction of motion or contracted. The amount of contraction will be calculated from the Lorentz transformation. The length is maximum in the frame in which the object is at rest. If you think about it, it's almost intuitive. Since the speed of light is constant, if the time is dilated in one reference frame, then space will be contracted. This gives you sort of an intuition about the process. For the sake of the argument, we'll call into action our superhero Batman and its Batmobile. Let's suppose Batman has a Batmobile and he wants to put it in his Bat garage. The Batmobile enters the garage and stops in it. The size of the mobile and garage are perfectly alike, and the Batmobile enters just the inside of the garage. Now let's suppose Batman has invited a new super engine that allows reaching comparable speeds with those of light. Then let's suppose that the Batmobile has an automatic pilot, and Batman wants to see how the automatic pilot parks the car in the Bat garage. So he's out of the car, standing next to the garage. The car is going at a constant speed comparable with c. Then Batman will see the Batmobile shorter than it actually is. We will notice that there will be a certain moment where the Batmobile will be a size smaller than that of the garage. And then when the Batmobile stops, it will be seen from the garage reference frame with its proper length, that is, the same length as the garage. Now let's suppose Batman itself wants to ride the Batmobile into the garage in order to park it properly. This time, Batman sees the garage is coming towards the Batmobile, so what he sees is the garage is shorter than when it's stationary. That is, the Batmobile is now longer than the garage. So there's a problem. How can the Batmobile enter the garage? Believe me or not, the car in some ways manages to enter the garage. In fact, whatever result we get by correct reasoning in any one inertial frame must be true. This means that in particular, it must be true when viewed from any other initial frame. And in our case, both are inertial frames, the Batmobile frame and the garage frame. In particular, if one is willing to do some math and physics, as long as the set of physical laws we are using is self-consistent and Lorentz invariant, then there must be an explanation of the result in every other inertial frame, although it may be quite different explanation from that in the first frame. And the explanation does exist, however it's a bit complicated, and thankfully we don't need it for the sake of this video. So this was the so-called garage paradox. Do you think special relativity is mind-blowing? Was this video useful to you? Let us know in the comments down below. Drop a like and let us know what you think. And remember to get ice cream before it's too late.